So far, all of our examples have been looking at indefinite integrals. So remember, indefinite integrals, that's just finding antiderivatives. We're trying to find the general family of functions whose derivative is whatever's on the inside of the integral. So that's why we always have the plus c. But what if we instead start taking a look at now indefinite integrals? What if we now try to say, what about the numbers? How do the numbers impact this? If we're using the fundamental theorem of calculus, which you should be using, the fundamental theorem of calculus says I simply find the antiderivative of the inside and then I plug in the numbers into there. So how does that work when we look at u substitution? So if we look at this one, the integral from 0 to 1 of x times x squared plus 1 raised to the 50x. If we try u substitution, we can. We pick that appropriately. Here, the choice is going to be x squared plus 1 because du is going to be 2x dx. So dividing over the 2, I have du over 2 is equal to x dx. I have something for x dx there. That's great. I have something for the inside here. That'll be good. So this is what we want. Now, when we see these numbers are saying x goes from 0 to 1. Because dx, x is my variable, x is going from 0 to 1. So when I try to replace u's on the inside, it's not the same thing as u going from 0 to 1. Those are different. So when we do this, we could write this integral, rewrite what we have. We'll have a 1/2 get pulled out from the du over 2. I have u to the 5th. I have du. But I will also change my bounds. My bounds in terms of x could now be solved for u by looking at this expression. So when x is equal to 0, so when x is equal to 0, that's our starting point. What does that correspond to over here? Well, just plug in x equals 0. Right? So u is going to be equal to 0 squared plus 1, which is equal to 1. So I now put a 1 there. And then when u is now 1, when x is equal to 1, u is equal to 1 squared plus 1, which is equal to 2. So again, I just plug that in. So now I go from the integral from 1 to 2 of u. By doing this, we'll see what happens at the end and why this is nice. So I integrate this, I add 1 to the power, divide by that. So I have u to the 6th over 6. I still have my 1/2 in front. Now remember, when we do this with definite integrals, we don't have the plus c anymore. That plus c goes away. I just simply write the 1 to 2. So I can simplify this. I have u to the 6th over 12 from 1 to 2. Now this, because these are u's goes from 1 to 2, I can simply plug this in. No different like I did with x's. So I have 2 to the 6th divided by 12 minus 1 to the 6th divided by 12. And that is my answer. You could simplify this with fractions if you want to, but not really a need to do that. Now, some techniques, if you don't like my videos and you're watching other resources, you might not even see this video anyways. But if you are watching this and you're looking at other ways of doing this, another technique that people will do is at this step, they might, when they go from down to here, they might have 1/2 integral of u to the 5th du, but then what they might do is they might say x equals 0 to x equals 1. Then they'll do the same thing that we did with our indefinite integrals by integrating this, then substituting x back in. So you'd have u to the 6th over 6, you'd have this, but again, you'd write x equals 0 to x equals 1, then you would substitute that back in, and then substitute those bounds in. I think that's just more work than necessary, so that's why I suggest changing the bounds. Then it's very easy that everything here is just in terms of the correct variable. That's my recommendation. So here, another example now, integral from 1 to 2 of x minus 1 squared over x plus 1 to the 4th dx. When we have a choice of picking our u, and we often pick things either numerator or the denominator, I will usually pick the denominator. That will usually be the go-to one. So I'm going to pick u equal to x plus 1. So I pick the thing inside the parentheses on the denominator. Then my du is equal to dx. The derivative of x is 1, so du equals dx. Now you might be thinking, wait a minute, again, we don't have x minus 1 squared, but this is that little sassy u substitution. I could now solve for what x minus 1 would be in terms of u. So if u is x plus 1, if I want to be able to get x minus 1, I could subtract 2 from both sides. If I subtract 2, I get x minus 1, and I get u minus 2. So I can substitute this in. Now, when we substitute in, we also have our bounds to worry about. So this is where we can use this to help us get our new bounds. So for our bounds, I have when x is equal to 1, u is equal to 2. And when x is equal to 2, u is equal to 3. So I'm simply plugging in 1 and I get 2. I plug in 2 and I get 3. So now I could substitute everything in. This is now the integral from 2 to 3. U minus 2 gets substituted in for the x minus 1. So I have u minus 2 squared divided by u to the 4th du. Now this requires a little bit more work. I can't integrate this yet. So one of the other techniques we have is algebraic simplification, right? If I just give you u minus 2, that's squared, that expression can be expanded by just multiplying out and combining like terms. So I can rewrite this. The integral from 2 to 3 of u squared minus 4u plus 4 divided by u to the 4th du. Then I can divide each of these by u to the 4th. So I have 2 to 3. I'm going to have u to the negative 2 plus 4 times u to the negative 3 plus 4 times u to the negative 4 du. So I just use my rules of exponents to say I subtract the powers of exponents by splitting this up into 4 different fractions. Because as long as the denominator is u to the 4th, you're really just looking at u squared over u to the 4th minus 4u over u to the 4th plus 4 over u to the 4th. This doesn't work if you have more than one term on the denominator. If you had something like u plus 1, you can't distribute that. Well, you could distribute it the same way, but you can't ever separate the denominator. Now I integrate each of these by adding 1 to the power and dividing. I get negative u to the negative 1 plus 4 over negative 2 u to the negative 2. So when I add 1 to the power of negative 2, I get negative 1. Divide by negative 1, I get a negative. Add 1 to the power of negative 3, I get negative 2. Divide by the negative 2. And then over here, I have 4 over negative 5, or 4 over negative 3, u to the negative 3. And this goes from 2 to 3. Then I plug in all of my constants now. So I have negative 3 to the negative 1. So that's another way of saying negative 1/3. I have minus 2. U to the negative 2nd will be 1 over 9. So I have times 1 over 9. Minus 4/3. I'm going to have a 1 over 27. So u to the negative 3rd is 1 over u cubed. 3 cubed is 27. So that's what happens when I plug in 3. Then I subtract off what happens when I plug in 2. Make sure you use parentheses. So now I have negative 1 over 2 minus 2 times 1 over 4 minus 4/3 times 1 over 8. Now you don't, I'm just skipping steps, right? Because you're on the video, you could go ahead and start working through the algebra on yourself and get to this step. I'm just skipping steps here, but if you should fill in middle gaps if you don't know how to go from one step to the other. And then if you'd like, you could simplify this, find common denominators, and just get some type of numerical number. That's cool. I don't really care. I'm fine to just leave it like this. You've gotten to the point where a calculator can just take the rest of it. So remember, what this number corresponds to, that's going to correspond to the net area. The net area from x equals 1 to x equals 2. So we have this region from from 1 to 2, and there's going to be some curve given by x minus 1 squared over x plus 1 to the 4th. Some curves given by that. This is the net area between that curve and the x-axis from x equals 1 to x equals 2. So remember, this is just a geometric statement about areas between two values given by some type of curve. So don't forget about that intuition. Same thing here. This is just the integral. This is just the area from 0 to 1 of whatever this curve looks like on this region, that net area between the x-axis and that curve. So use substitution with numbers, our definite integration.